All right, so the things we talked about so far in terms of the technical details with the midterm coming up tomorrow is part 1. It'll be Canvas graded. It'll look just like those Canvas quizzes. This one will have responders attached to it, so you want to make sure that you've got all of that app downloaded or program downloaded, so you're all set up. In terms of what it's going to be, I'm likely going to have this thing timed. It's only going to be open for a little bit longer than this time. I'll open it somewhere between 11 and 11:15 a.m. and I'll close it down. I'm thinking probably around 12:30. And this is really so that you still have enough time to do part 2. Okay. So that was the main thing there. I'll set it up so that you can also come and talk to me in WebEx. The only issue that we found so far was that log into WebEx first and then go over and do the Canvas quiz. If you go it the other way, it's 50-50 whether you can get in or not. And we have not figured out what is the thing that makes that work or not work yet. I actually had one of my preceptors in the spring, we tried to demo it, and we couldn't figure out what setting had been flagged or not flagged, where some people could get into it and some people couldn't if they didn't log into WebEx first. Part 2, free response, I'll upload a PDF that you guys can either download or you can write out on your own piece of paper. If you write it out on your own piece of paper, please put each question on its own piece of paper. That way it's easier for me to grade, because I'm not going to lie, grading uploaded stuff takes me about 3 times as long as grading a normal test. So just grading the 2 questions that you're going to have here is probably going to be the same amount of time as normally it would take me to grade the entire test if it was all on paper. So please, please, please make sure if you're going to copy it out on your own piece of paper, either copy it exactly how it was written on the PDF on your piece of paper, or one question, the graph at the top, and then all of your work below. Okay. And I'll open this one up somewhere around 12 to 12:30, and I'll have it shut down between 1 and 1:30. It'll probably be 1:15, 1:30 when it'll shut down. And this close here is you've got to upload your file before it closes, or it will not accept the file. There's no timed anything on here other than the fact of when it opens and when it closes. Okay. All right. So that takes care of the technical details, and of course the program froze on me. So just a second, let's see if we can't get that. There we go. All right. So then the extra questions were about duals. All right. I've now forgotten what all those questions are, and I'm not going to assume that I can go back and find them in the bazillion questions that we've had so far. So to remind ourselves, the 2 or 3 of you that sent in the questions about duals, was it just going over another example of how to find the dual? That's what I'm remembering in my head. I want to make sure there wasn't anything more than that. All right, so far I'm getting yeses. So let us grab an example. So remember, you're only going to have a dual if you have a planar graph. So maybe you have something like this guy. And then maybe you have, oh, I don't know. I'm trying to think of something more. Realistically, if you got one of these questions on the test tomorrow, it probably would just be a simple planar graph. In that case, it would be something similar to this, and maybe we make it a slightly more interesting. Maybe we have it like this. This looks kind of fun. You could do something like this. There we go. I was trying to get away from doing curved lines. Oh, well. So here we've got, and actually you don't even need to label these vertices to be able to find your dual. Since we've been labeling vertices, let's go ahead and do it. So suppose you're given this guy. Okay? Now, the easiest way to find a dual is you go in and you put a dot for every face you have. So here we have what? We have a face right here that looks like that square. We have a face right here that looks like this triangle, or this, if it looked like kind of looks like a building to me, like the roof of the building. So I'll go ahead and label these 2 as face 1 and face 2. Now I'm going to claim we have more faces. Anybody spot another face? One of them being the unbounded face. Anybody spot any more faces? A, B, yep. So there's a face right here, and there's one more face. Anybody spot the last face? Yep. And the last one down here is that other sort of bubbly looking one. Okay, so we've got 4 bounded faces and we've got the unbounded face outside it. Okay, now if you're reading this in your book is perfectly fine dealing with the bounded faces, but for whatever reason he doesn't deal with the unbounded face. I don't know why. Okay, so here if you go, what do? The key thing next is you want to put in the edges. So in your dual, what happens? All of the new vertices in the dual were the old faces in the original graph. Now, the edges in the dual, these guys are perpendicular to the edges in the original graph. So here, notice what happens. Every edge that you have in this original graph, you're going to have some line that crosses it. And that's the key thing. Exactly one line that crosses the original edge. So for example, if I'm looking up here at face 1, it's enclosed by 3 edges, which means there's going to be 3 edges now that are incident to the vertex indicated by F1. So we've got one of them that crosses the line CD. And it's standard to put dotted lines, likely just because we often write only in pencil. But if you're color coding, it's up to you whether you want to do dotted lines or not. Then we've got one edge that's going to cross AB. And when you cross AB, now we're in face 3, so we'll go ahead and connect this guy over to face 3. And then we have the last edge of this face 1 was AC. So in the dual, you're going to have an edge that goes through that edge AC. And this guy now is outside your graph, so he's going to connect to the unbounded face. Okay? And you do the same thing for all of them. That strategy right there, as long as you then pop on to each and every one of your faces, will get you to the entire dual. So for example here in face 2, how many edges are going to be incident to face 2 in the dual? Almost. So face, yep, now you're good. So I've got the one we've already drawn. We also have, if we look at the original edge BE in the original graph, in the dual we'll also have an edge that crosses that. The edge will go from face 2 to face 3. We'll also have an edge that goes from face 2 to face 4, crossing through the edge DE. And then our 4th edge is going to be going through this edge CE. So this will be face 2, but then it's going to go and attach, well, down here to face 4. Okay. So that takes care of face 2. Now when we then look at face 4 down, actually let's do strategic. If we go to face 3 over here, it's got how many edges? 1, 2, 3, 4 in the original graph, which means there should be 4 edges incident to it. Well, one of them is going to be going through that original edge EF in the original graph. So that guy, that's our curvy. And then notice, because one of these edges here touches the unbounded face, you'll also have an edge that goes through AF and goes over to that unbounded face. Okay. Now, are there any edges left in the dual that we haven't drawn in yet? If so, who do you think it is? Well, CF is not an edge in the dual. It is, however, an edge in the original graph, and that is the edge we want to cross. So in the dual, the edge would actually be F4 to F infinity, but yeah, you totally cross through CF and get this last edge. Now, quick check. Do we have all of the edges drawn in for the dual? All right, now, how do we know for sure? If we actually went over here and did a little chart, here's the original graph, here's the dual of the graph. There's always the relationship. So if we look at the vertices in the original graph, we had all those letters. And then we look at the vertices in the dual, and it's all of the F with a subscript. Well, it's easy to count up how many vertices are in the dual. In the original, it looks like there's, make sure I count them up right, it looks like there's 6. You guys count 6 vertices in that original graph? If not 6, we need to change it. All right. So next we want to go ahead and count up the edges. So in the original graph we had 1, 2, 3, 4 for the square, 5, 6 to get the triangle, 6, 7, 8, 9. Now, supposedly, we'll have the same number of edges in the dual, so quick check, do we have 9 edges in the dual? It looks like 9 to me. Well, even if it's not 9, even if we miscount, what do? Every single one of the edges in the original graph is crossed exactly once by one of these dotted edges in the dual. So we definitely have the same, even if we miscounted the 9. So I'll go ahead and pretend we did right on the 9. Now, in the dual, take a guess here. What do you think? How many faces are in the dual? Okay, we might have miscounted the number of edges. But let's deal with faces first and we'll go back to edges. So in terms of faces, we should be getting 6 because it's supposed to be the same number as the number of vertices in the original graph. So let's check. Got 1 here, got 1 here, so that's 2, 3, 4, 5, and then the unbounded one, there's 6. Yep, so it looks like we're good with 6. All right, so let's double check our count here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm getting 9. All right. Whew. I was worried there because I got 9 when we counted them up on the regular graph, but I hadn't bothered to count in the dual. Okay. So that's the crash course in dual. We haven't done any applications with duals yet, but they do come into play when we get to the end of chapter 2, but we're not going to get to that till after the test. But that's the basics of duals. You wouldn't really have anything much more complicated than that on the test. The main thing that you'd need to be able to do is you need to, if you're given a graph, know if it has a dual. So that means it's planar, there's no crossing edges. You'd need to be able to construct the dual. I would prefer if you then draw it out to the side, but if you left it just like this, I would take it if it's right. And you'd probably be asked things like, hey, what's the number of vertices, number of edges, number of faces? Maybe like on one of your quiz questions, I think on one of your quizzes you were asked something like adding in an extra edge, but that may have been with a different question. Okay. But that would be that's the basics of a dual. And really the only big differences you get is how complicated that planar graph is. Okay. Other questions from you guys? It depends on the graph. So let me go into black writing. So strategy for isomorphic. I would definitely first step, look at your number of vertices and edges. Definitely, like hands down, that's the first step. Now, once you have all of those looked at, something that people will often put somewhere either as a second step or as a third step, and I'm not actually going to write it down as a second or third step. I'm just going to put it sort of as a bubble over here to the side. Actually, I can put this as like a flow chart if that helps. But over a bubble over here to the side, people on simple graphs will start looking at, can I move the vertices of one of the graphs, so let's say of G1, to get the other graph, let's call it G2. Okay, so that would be something that would be, if you have a small and tiny graph, that might be something where you start looking at, oh, maybe I can move some of these vertices and actually create the other picture. If you can, that would mean you're isomorphic, and you'd need to go and grab an isomorphism. But the real second one is look at the degrees. Okay, and at each one of these stages, so here, if everything matches, so if doesn't, so I'll put this over to the side. So if anything fails, stop. And the result is the two graphs are not isomorphic. And let me go ahead and get rid of that one. Okay. But now that you're really on your step 3 here, this is where things start changing, okay? So let's put this as categories. So we looked at, I'm trying to move it so you can see everything at once, and it's just not working for me. So over here, if you have at least 2 different types of degrees. Okay, so the example that we did in classes, we had a bunch of degree 2 vertices and a bunch of degree 3 vertices. But if you need to have not all the vertices are the same degree. So you have at least 2 different degrees that you're dealing with in your graph. And you need to have at least one of those vertices and at least one of the degrees that's in play in your graph is have a number of vertices involved. So has many vertices. Now when I say many, something like 3 or 4 is still perfectly fine for many. Okay? So that's the check. If that's the case, this is where you use subgraphs. Subgraphs would likely help at this stage, okay? If you've got more than 1 degrees in your graph, and you also have at least one of those 2 degrees or more than 2 degrees, have several vertices all having the same degree, okay? And then you take a subgraph, and specifically here, you're taking all vertices of the same degree is the key thing with this strategy, okay? So that's one thing to look at. And this is something that it's frequently that you can do this. This is actually a pretty common thing to do. It's not the most, I don't want to say it's the most common because there's not really a most common thing to do, okay? Now, maybe you don't have this situation, okay? So maybe you start looking at something else. And what's something else that we saw? Something else that we saw was when we did complements. Well, when you do complements, that's only advantageous to you if you have enough edges, okay? So if your graphs have more than half the number of edges on the complete graph on the same number of vertices. So if you have n vertices, so say you have 4 vertices in your graph, then you need to have more than half the number of edges from K4. If you have a graph with 11 edges, you need to have more than half the number of edges that would have been in K11. Okay? If that's the case, then you go down and you look at the complement graph. Now, fair warning, wow, I can't spell complement today. Fair warning, when you're looking at the complement graph, just like when you're looking at subgraphs, you are then checking to see if those subgraphs or that complement graph, if those guys are isomorphic, okay? So that means you start the procedure again on the subgraphs or this complement graph and check if they have the same number of vertices, do they have the same number of edges, and then maybe in the complement graph, you can go with subgraphs, hint, you won't be able to because you're going to say debris spread is in the original graph, okay? But you start seeing if anything helps here. Now, those 2 would be ones that I would recommend checking first. It often has that these 2 guys will take care of what's going on. Yes, I'll go ahead and post all of these notes after class. Okay. You could, so it depends. So the question is about bipartite. So if it's really obvious that one of the 2 graphs is bipartite, so let me do sort of a third thing over here. So if one graph that was trying to be the number 1 is bipartite, then you might check, is the other one also bipartite? Now, if it's not obvious that either of them are bipartite, that's probably not something that you'd necessarily check first off. That would be something like 4th time down, and you're like, I'm just convinced these 2 graphs are not isomorphic. Let me check bipartiteness, okay? In terms of how many isomorphism questions, you're looking at you're probably going to get one of them that's just straight up here, two graphs, are they isomorphic or not? You might have something that, a second question if they're two really tiny graphs, and maybe ask some more about it. But in terms of the question where you're actually given the two graphs, and then just the blanket question, are these guys isomorphic or not? No, you're looking at just one of them just because these guys take a little while to get through. Okay. What else did we talk about? We also talked about circuits. So when you start looking at these guys, if you notice, say, a circuit that goes through all the vertices, like a Hamilton circuit, that would be something that's distinct. So you'd say, hey, well, is there a Hamilton circuit in the other graph? So here. Or maybe you find that there's exactly two circuits of length 4 in one of the graphs. Well, if there's exactly two circuits of length 4 in the other graph, that's something. It's definitely more helpful if these things fail because you get the immediate answer of not isomorphic. So here's the sort of rule of thumb. If everything works, and by this point you've already checked, say, 2 to 3 things, and when I say 2 to 3 things, I mean 2 to 3 things down here, or maybe just one thing down here. This is where you need to start thinking, hey, the graphs are isomorphic. So maybe the graphs are actually isomorphic to each other. And in that case, what you would need to do is you would need to build the isomorphism. The two things that help the most with building your isomorphism is there's some distinguishable, or some distinctive, I should say, distinctive circuit, or the degrees are really nice. If at that step 2 at the top where you're dealing with degrees, if you've got the degrees are all distinct, go and check the isomorphism right there. No, if you don't want to check everything, don't worry about it. Once you've checked at least one thing down here, maybe a second thing down here, that's when you, and it works, everything's the same between the two graphs, don't keep checking things ad forever. Go and say, hey, I think this has an isomorphism, and try building your formula or building your function based off the information you have back here. So this information of your subgraphs and your degrees and your complements if you did complements, your bipartness if you did bipartness or your circuits, that's going to help you tell which vertex has to be mapped to the other vertex. And that being said, there's rarely one isomorphism that works across the two graphs. If the two graphs are isomorphic, you typically have several of them, which is always fun to find a new isomorphism in the middle of grading. But that happens almost every summer. I only teach this class in the summer, so almost every time. So that gets, those are the big things. The complements and the subgraphs and the circuits are the big things. But any distinctive property that you can find in one graph, if that distinctive property is not in the other graph, that would make them not isomorphic. But that gives you a little bit of an idea of when you would decide to do which thing. But yeah, don't assume that you have to do all of these different checks. As soon as you get down here to this second level after the arrows, I would, depending on time, I would probably go with one, maybe two of these things, and then be like, hey, if everything matched, just go try to build the isomorphism. Because building the isomorphism does actually take a little bit of work, so you got to worry about time on that sense too. All right, let's make sure I didn't miss any questions. Got that one, got that one, got that one. All right, I think I answered all of those questions. All right, other questions from you guys? Yes. So the plan for today was to finish up section 2.2, and one of the last questions, and it looks like I'll go ahead and just record a small video of the second example for you guys, but one of those questions is dealing with what you're talking about. I don't recall if the example actually didn't have the Hamilton circuit, but it definitely, we can talk about that as we walk through that last question. Yeah, no. I would say in terms of figuring out if you can find a K5 or K33 configuration in planar graphs, I would start with the circle chord method, if possible. If you have the circle chord method, draw a picture of what K5 and K33 look like in that same circle chord orientation, and that helps with the guess and check. But finding the K5 and the K33 configurations to show that somebody's non-planar also works if the circle chord method fails. Namely, the circle from the circle chord method is one of those Hamilton circuits. So if you don't have a Hamilton circuit in your planar graph or your non-planar graph, which happens all the time, you got to look for your K5 and your K33 configuration. Here's one way to do it. It's off of degrees. Okay, so what you'd be looking for here, K5, you need 5 vertices with degree 4. Now, if it's actually K5, those 5 vertices are the only 5 vertices in your subgraph. If it's a K5 configuration that's not K5 itself, you'll have extra vertices involved, not just the 5 main ones. Okay. No, if you're able to use circuit chord method, that is sufficient to prove non-planar. Okay, it is 100%. It actually does the same thing of the K5 and the K33 configurations in there. That's perfectly fine. But if you can't find that one single big circuit that goes through all of the vertices, and you have to look for K5 or K33 configurations separately, this is where things get crazy. I'm not going to do that for you on the test, okay? And on the test, if you have to prove somebody's planar or non-planar, you should be able to use the circle chord method. Okay? Should is the keyword there. All right, so if you're looking at a configuration for K33 configuration, this one here, you need 6 vertices, and each of them have degree 3. Okay. Again, if you're just going to find a copy of K33 that's a subgraph that's not a full configuration, you'll just find your 3 vertices of degree 3, and they have to actually connect back to each other with all those edges. But if you're doing a proper configuration where you have extra vertices involved, those edges that are attached to your 6 degree 3 vertices don't have to go directly back to the some other vertex in this set of 6. Okay. But that would be sort of a way to start finding your configurations is look for your collection of either 5 or 6 vertices with degree 4 or degree 3 across them. No lies, it does take some practice finding these guys. But that's why it's homework. That way you have a little extra time to start grubbing through it. Other questions from you guys? All right, I haven't seen any new questions come in from you guys recently, so I'm going to assume we have exhausted your questions. I will go and update that because I don't think we're going to get to gray codes today. And if we don't get to gray codes in the next 10, if you see something with gray codes, I would define it, is what I'll say. Because that is actually at the end of section 2.2, and we'll talk about that today. So let me do 2 things with respect to section 2.2 today. We had several examples that dealt with showing if you don't have a Hamilton circuit. So let us look at another example here. In terms of the grade code question, if you had something on there, the most you would have is an identification, and I give you what the definition is and say, hey, did the thing that we just do, does it meet this definition? So that would be the most you'd see from it. Okay. All right, so let's look at this. So where we ended last time was dealing with rules of how to build a Hamilton circuit, what you had to actually have. Specifically here to remind ourselves, if you had degree 2, when you're building that circuit, you had to use both those edges because you went into the vertex and you left and went out of the vertex. You weren't allowed to, when you're building your circuit, go back and cross on itself, so you couldn't go and visit a vertex a second time. And Well, these two are actually related. The proper subcircuit means you come back and cross on yourself again, and you're not allowed to use a vertex more than once. So this here tells you that, hey, when you go through a vertex once, you can then cross off the edges that are now can't be used because you've already gone through that vertex once. Okay. So we did this little itty-bitty baby example last time. So let us look at this slightly larger example. Okay. But here's what we want to do. We want to show that this graph actually doesn't have a Hamilton circuit, and it doesn't say any old Hamilton circuit, because we could actually find a Hamilton circuit. Maybe. We'd have to play around with it a little bit, but it looks like we'd be able to go back and forth to be able to find a Hamilton circuit here. Okay? But this, we want to show that this graph doesn't have a Hamilton circuit that uses the two edges AF and CH. Now, to make our life slightly easier, let me highlight AF and CH. So AF is this guy, and CH is this guy. Okay, so we need to be able to use those two guys. Okay. Now, if we want to go ahead and use this one, let's start off and look to see what we can do. Well, we like to start at A, so we need to use edge AF, so let's go ahead and actually figure it out. Now, if we look at our rules, I'm going to go ahead and circle A here, start at A. If we look at our rules, it's first rule 1 says take any of your degree 2 vertices. Do we have any degree 2 vertices right here? What do you guys see? Do you see any degree 2 vertices here? A and C. I don't see a degree 2 at A and C. Oh, after you remove this edge. So it looks to me like all of these look to be degree 3, so that first rule, not going to be applicable. Now, the second rule says don't build a proper subcircuit. I can't do anything with that one yet. And the third one says once you use two edges that are incident to a vertex, in other words, once you pass all the way through, you're not allowed to use any extra edges that are incident to that same vertex. So we said we wanted to start at A. So if we start at A, we'll here have A. I'll just do the highlighting. A, and let's say we go to B, okay? So no worries there. That could be the first edge in this guy. Okay? But what does that mean about vertex A? If we have to use AF later, and we just used edge AB right now, that means you can't ever use edge AE in the future. Okay? That's all it says. Now, if we're now here at B, let's see where we would go next. If we go next, we could either go to C, but if we went to C, we still have to go back and pick up G, and then once we get to G, well, there's no real place to go. Let me go up and highlight again. If we did something like that, once we got to G, either going back to B, we'd form a subcircuit, or going to F, we'd form a subcircuit. So that's not really something that's, we're not going to be able to do that. So let's go back and get rid of those last two edges. So instead of doing the edge B to C, let's instead go B to G. So we picked up G, no worries. According to our rule 3, at B, we've already used two edge incident to B, so we'll go ahead and we will cross off BC. Okay? So that's how we'd use that rule 3. Now, once we're at G, we went to F, we close the circuit, but if we go to H, no worries, that's just fine. Okay? Now notice, are we ever going to use the edge GF? What do you guys think? Will we ever use the edge GF in this circuit we're currently building? Nope, not unless we change some of the edges we're using. So let's go ahead and cross that guy off to remind us. Now, notice what this means. If we say that F to A is the end of the circuit, notice at F, we have to use this edge that we already said we were going to use. We just crossed off that edge. That means the second to last edge that we would cross would have to be over here to J. So you can actually build this circuit from both directions if you want. Okay. I'm going to go back to C. So for C here, notice we're not allowed to use that edge because we close off the circuit right here. So there's only one option. You have to go forward to D. And let's cross off some of the edges that we can cross off that we should have crossed off earlier. Back here at H, we already went through H, so H to I is not going to be an edge we're going to be allowed to use. in the future. Okay. Now, at this point, coming back to vertex D, we have a choice. We can either go to I or we can go to E. Which would you guys like to do? You want to travel from D to I or from D to E? You want to go to I or to E? All right, I got a vote for I. That was actually the one I was thinking too. So if we go up here to I, whoops, what does this tell you? This tells you, according to Rule 3, we're going to have to, we already have included 2 edges incident to D, so the third edge incident to D has to be removed. Now, once you're at I, notice you're forced to only go in one direction right here. And to go in the one direction right here, what happens? We're going to, oops, wrong thing. We're going to have to go and connect I to J. Okay? Now, once we've connected I to J, notice what happens. What just happened? You guys tell me. And while you guys are typing or thinking, I'll go ahead and explain what we did here. So what happened? What did we end up with? Remember the highlighted parts in yellow there, we're trying to FJF. Yeah, so actually I should probably put this in slightly different colored. The 2 edges we were originally told that we had to use were these 2. So we were trying to build a Hamilton circuit that grabbed those 2 guys. And previously, what we had done when we were about halfway through building or collecting these highlighted edges right here is we had went back and said, hey, because we crossed off and we weren't allowed to use G to F from earlier, that meant the second to last edge that we had to be the F to J edge. So that's something that when you're going through these things, you can work from the beginning point, or you can work from the end point, or like what we did here, we did 2 edges at the end, and then most of our edges were coming from the starting point. There's not necessarily one Hamilton circuit. You can have exactly one. You can have multiple ones. Okay? Now, when we did this, notice what happened. Did we actually build a Hamilton circuit? Now, what's the problem with the thing we built? What happened here? Because we followed the rules. Well, Rule 1 wasn't applicable because there's no degree 2 guys, but we followed the Rule 3 that said, hey, as you go through each of these things, cross off the edges, you're not allowed to use again. We didn't close up any little sub-circuits, but yeah, we never reached E. So technically, when we got all the way back here and we closed this guy to get back to A, we actually did form a sub-circuit. So, whoops, I can't write with a highlighter very well. So this one here is we formed a sub-circuit. In other words, because we missed vertex E. And if we had gone at vertex D to E instead of vertex I, we would have missed vertex I. So you would have gotten the same conclusion right there. So this one here, this guy was violated. Now, since the rule was violated, and we didn't do anything wrong, we did everything we possibly could here. If we redid the edges and did it a different way, maybe some of these edges we could have switched around, but you would have gotten the exact same conclusion each time. So this gives us a conclusion of, and I guess is what the conclusion should be. What conclusion should we come to about this graph and Hamilton circuits? Don't overthink it. Yeah, you're actually going to get that no Hamilton circuit is going to be able to exist because the Hamilton circuit has to pick up all of your vertices, and however you reform this one, you can shift it around, maybe rotate it around, but you're actually going to end up each time missing at least one of the vertices, and that is, yes, as one of you said, with these constraints, you won't have a Hamilton circuit. So no Hamilton circuit exists. That also includes your edges. What were the two edges? AF and CH. So that's the conclusion I get to. Okay? Hopefully that helps a little bit in figuring out when a Hamilton circuit doesn't exist. When a Hamilton circuit does exist, it can just be tedious to find it. Okay? Make sure you explain which rule was violated and where it was violated. So in terms of the homework for this section, yeah, you would go through the same procedure. And when you started getting the rule violated, and note, it's not just at the very beginning you violate the rule. You're forced into violating the rule. Say which rule was violated, say where the issue happened, and then, yeah, that's all I'd be looking for. And some of them in the homework are relatively straightforward, but one of them is a little bit nasty. Other questions? Hopefully that made a little bit more sense to the Hamilton circuits. Yeah. If you do like what we did strategically in here, where first you grab all your all your vertices with degree 2, add those edges, and then you get all of your vertices. You start traveling through the graph like what we just did. Yeah, rule 2 gets violated a lot. The only exception to that is if you have a ton of degree 2 vertices, or you have degree 2 vertices oriented in your graph in such a way that you can't not use them. You can get issues where the degree 2 vertex will cause rule 3 to be violated. That occurs. Oh, good, I have some space. So here, maybe you have something like, here's a degree 2 vertex. Here's another degree 2 vertex. Maybe here's another degree 2 vertex, like this. And in this particular case, notice if you have to include all of your degree 2 vertices. And when you get that last one, all of a sudden issues right there because you had to include your degree 2 vertices. And that would be where rule 3 would be violated, and that's the interplay between rule 1 and rule 3. But yeah, if you're able to get rule 1 and rule 3, and often we can, rule 2 gets violated a lot because you just are like, I can't get any further. I have to close off that circuit. Okay. Other questions? Kind of make sense, hopefully better. All right, so I'm just going to show you what's the last thing, but I'll go ahead and put this into a little video. There's 3 theorems, theorem 1, 2, and 3. We're really honestly not going to use theorem 1 and 2 all that much. They're just interesting, so I'll put it in a video. You can watch or read it in the book. And then theorem 3 is actually kind of interesting. And this one here, I had set up an example to show what it really meant. But again, we're out of time. I'll just throw that into a video because for the grand scheme of the course, none of these things are not things that we're going to use a ton. Okay. But that's it for today. We'll start in on section 2.3 then on Wednesday. No, these theorems would not be on the test for tomorrow. So the only thing in section 2.2 that you'd need to worry about is make sure you worry about how to find a Hamilton circuit or path. And I think that's the only big thing in this section. Make sure there's nothing I forgot. Nope. Just make sure you can find a Hamilton circuit or path, and that's what I'll look for in terms of this particular section of the test. That's a possibility. If it's something that you do on Canvas, you'd need the curly braces for the edges. If it's something you wrote on paper, I'd probably take them either way. And that's just because there's only so many answer possibilities that I am going to write into Canvas for it to accept. So watch out for the directions on what to write into the Canvas form. It'll be on each question.